Mazda's new 2.0-litre Skyactiv X engine is the world's first production petrol unit to exploit the benefits of diesel-like compression ignition. Key to its operation is the use of a highly lean, fuel and emissions-efficient mixture of air and fuel, 2 to 3 times leaner than in today's conventional engines. This mixture has so little fuel in the air that a normal engine with spark plugs cannot fire it. Mazda already uses uniquely high compression ratios on its current Skyactiv gasoline engines to reduce fuel consumption. This leads to the idea of increasing the compression ratio even further and igniting the fuel simply by compression, as is the norm in modern diesel engines. This concept has been tried before by several manufacturers with homogeneous charge compression ignition (HCCI), but none have been able to reliably switch between compression ignition and spark ignition. Mazda's unique solution to the problem is Spark-Controlled Compression Ignition (SPCCI), which allows the engine to switch seamlessly between conventional combustion and compression ignition by using a spark to trigger both types of combustion in different ways. Here's how it works. A split injection process creates 2 separate zones of fuel-air mixture inside the combustion chamber when it switches to compression ignition mode. A series of injections first flood the combustion chamber with a lean mixture of fuel and air with a high proportion of air. During the intake process, then precisely inject a richer zone of atomized fuel directly around the spark plug during compression. Imagine a cherry on a cupcake, where the cherry is the richer zone and the cake is the lean mixture. Because of the high 16:3:1 compression ratio of Skyactiv petrol technology, the first charge is on the verge of spontaneously combusting anyway. To ignite the mixture at the right time, a small injection of atomized fuel directly around the spark plug builds a richer core. When the spark fires, it ignites the local zone of fuel and air. This increases pressure in the combustion chamber to the point where the lean mixture combusts. SPCCI works only at part load. During gentle driving and with lean mixture, a much greater proportion of air to fuel than in a normal gasoline engine, improving fuel economy. However, when the driver asks for more power, the engine seamlessly switches to normal operation ignition, igniting a conventional stoichiometric fuel and air mixture of 14.7:1. Conventional combustion is used only under high engine loads and during very cold starts. Through control by the spark plug, the issues of knocking and unstable combustion can be avoided, achieving a seamless transition between compression ignition and spark ignition. When the engine is running in compression ignition mode, it uses less fuel and produces less CO2.
I'm Jamie Turner. I'm Professor of Engines and Energy Systems at the University of Bath in the Institute of Advanced Automotive Propulsion Systems. I do a lot of research on alternative engine concepts, a lot of research on alternative fuels, and linked very much to that, I do work on decarbonisation of liquid fuels. The sensible thing, as far as I'm concerned, is to pursue all the available options that we have, and that has to include the internal combustion engine. The internal combustion engine is a remarkable piece of equipment, really. It's enabled the modern world in many respects. We've been building it for 120 years now. It's affordable because it's made from cheap processes, and it has a cheap energy storage system. We really need to look at things in terms of well to wheels. Above that, we need to move to what's called life cycle analysis, because at that point you bring in the difficulty of getting hold of all of the raw materials and the processes involved with making a car. At the moment, the manufacturers are responsible for the tank to wheel, and the fuel companies are really responsible for the well to tank part. The legislation raised on the car manufacturers is actually very, very severe year on year. We've got to get down to 95 grams of CO2 per kilometre, and that's going to be incredibly difficult using current technology unless we develop new combustion processes. Downsizing is a very good way of getting fuel consumption, but essentially it really brings you benefits on a drive cycle which is very light. On less easy drive cycles, it's not such a benefit. There's definite argument for having a slightly bigger engine. And in that respect, there is this phrase right sizing that is now used, something that is the right size for what we need. Definitely that has come towards Mazda. HCCI, type combustion systems, they don't burn with a flame. If you just get something and squash it enough, it will ignite. The compression heat initiates combustion. So if you don't have a flame, you don't have the very high temperatures locally to create NOx. So the real attraction of these combustion systems that have really got people to work on them is twofold. Good fuel consumption, because you're running very lean, and secondly, the promise of negligible NOx output from the engines. So we've all known that that would be the panacea if you could do it. It's been spectacularly difficult in a four-stroke engine. People have looked at different things, and the Mazda system uses mainly a charge in the engine which is very, very lean, prepared with an early direct injection event. And then towards the end of compression, they inject some more fuel very close to when they want to ignite it, so it's very close to the spark plug. They pass the spark, that ball of ignitable mixture burns, and it expands. When it expands, it compresses the rest of the charge, which then goes off in a compression ignition process. Mazda, with the SP-CCI system, seem to have made a breakthrough. And they've done that by really combining elements of spark ignition with elements of compression ignition. Of course, that's the theory. I think we can safely say that if we could have done it before now, we would have done it before now. And that's why it's important that someone's been first. And for me as a researcher, having worked in this area for 15 years, it's going to be very interesting to drive this car and see what it's actually like on the road. We really are going to need a portfolio approach in the future. There's no doubt that the internal combustion engine will continue to play a very major role for most manufacturers. Electric vehicles are great in terms of no CO2 emissions at point of use, but nevertheless, we have to make new technologies that run on fuels which are in the market now. And that's why this particular combustion system is potentially very important. But we do need to keep improving them so that we can reduce the emissions from road transport and hopefully mitigate climate change. When you drive it, I'm very impressed with the way it starts, and it seems to want to go into SP-CCI pretty much immediately. It's got quite a lot of low-down torque. It holds gears well. It's also very quiet, and that's a definite surprise, I think. I'm impressed with the control that they have over the combustion system. Plainly, the development of the combustion system by Mazda has yielded something new. I think that for the man in the street, they wouldn't honestly know that it was any different to a gasoline engine vehicle. As far as the drivability is concerned, it's Really, really very good. The 96 grams of CO2 per kilometre that's officially claimed for this is extremely good, I think, in this class of car with this performance. Fuel consumption, I did 43 miles per imperial gallon, that's about 6.6 litres per 100 kilometres, which I would think as being very good for a gasoline car of this class. As we move into the future, we need novel engines. Engines will be around for a very long time yet. It's really quite interesting from the perspective of someone who's worked in the industry for a long time. We tried a very long time to do this, and no one's ever really managed to do it, certainly not in production. There were moments when I thought, no one's going to do this in a four-stroke engine. It's just too hard.
Moreover, because SPCCI is so stable whereas HCCI wasn't, it can be used more frequently in the engine's operating range, which means the engine can run more than 80% of the time in a very efficient mode. As a result, fuel consumption is 20% less than that of the Skyactiv G, and torque is increased by 10 to 30% depending on RPM. With improvements being especially great in the light engine load range, Skyactiv X improves fuel economy and reduces CO2 and NOx emissions. Challenging the commonly held belief that medium-sized petrol engines have pure fuel economy in cities. Combining the advantages of both petrol and diesel engines, SPCCI offers power, acceleration, and environmental performance, making Skyactiv X a great alternative for those who prefer petrol engines with the benefit of diesel.